Hey everybody, it's Mr. Keeney once again. We are on to our last section of notes for Unit 1. And again, as a reminder, Unit 1 is all about developing our foundations of geometry, using that vocabulary, using the undefined terms, point, line, and plane. Today's I can statement, so the next kind of topic for us is classifying polygons. So you can kind of see where we started, points, lines, and planes, and we're kind of putting things together to create segments, angles, and today we're going to put even more of those together to create polygons. So first thing is talking about what is a polygon, and I know that this is not new to you. You've dealt with polygons before. In this class in geometry, we're going to consider a polygon a closed plane figure. So a closed plane as in what the plane we've been talking about, not the plane like airplane. It's a closed plane figure, but it does have certain properties. Number one, it is formed by 3 or more line segments, and we will call those, and this should not be new, sides. And notice that it says line segments, so we're dealing with what we would call, I guess, in non-math terms, straight lines, but we're going to call those line segments with endpoints and all the points in between. Each side intersects exactly 2 sides, one at each endpoint, so that no 2 sides with a common endpoint are collinear. So basically what this means, and I kind of mentioned it without really thinking about where I was going with the statement, but that's if we have a side of a polygon, it is going to intersect 2 other sides. And where they intersect, where they always intersect, is at the endpoints. So those endpoints, and this kind of goes into our next one, we have another name for them when they're a part of a polygon. They are called a vertex. If we ever talk about multiple, plural, I guess the plural version of vertex is vertices. So if I'm talking about vertex A, B, and C, I could say vertices. A polygon can be named by listing the vertices in consecutive order. So here's an example of a polygon down below. If I wanted to name this polygon, something I could write as polygon. And then if I start at A, I could say A, and then go to B, and C, D, and E. I started at A, and I went clockwise. I could also start at A and go counterclockwise. So A, E, D, C, B. But the big thing is, if I'm starting at A here, I'm going to go to B next, C next, D next, E next. So that's one way to do it. The only other way is A, and then I go counterclockwise in this direction. But don't be skipping around. Don't do like A, C, D, E, B. We want to make sure that we are going in order. So that's kind of our notation rules for polygons. It'll be the same thing for all polygons. So whether it's a triangle, whether it's a quadrilateral, heptagon, whatever you want to say, it will be the same. Now, as far as polygons, they can be classified, and they can be classified in a bunch of different ways. Here's one way we can classify them. We can group them into 2 different types. We could say that they are either, oh, I got the wrong pencil here. We could say that they are convex, or we could say that they're concave. And so I'm assuming this is something maybe you've heard of before. I'm not too familiar with the middle school curriculum, being my first year here, but I'm comfortable in saying that convex and concave is something that, even if you haven't heard, I'm confident that we're going to be able to get this. I like to start with concave in describing what this means. Of course, when we're younger, we might think, oh, it caves in. But I want to make sure that you know the geometric idea of how can I tell it's concave. And with concave, I'm going to look at all the sides, and I'm going to look at this one right here. Here's a side. And if I were to continue this side and make it a line, you'll see that it intersects another segment. And that is what calls it, or what names it, a concave polygon. Because if I extend that side, if I extend this one, it's going to hit another side right here. So that is kind of why we classify it as concave. If you look at convex, it doesn't matter which side that I extend, it will never intersect another side. So this is kind of what makes it convex. I could extend those into lines, and it will never intersect another side of the polygon. Where if I look at concave, if I extend this one, or if I extend this one, you can see we get some no-nos as far as, nope, we cannot do that. it is concave. I guess we could do that. It's just meaning it's concave. Another way to classify are polygons. And this is talking about the two things that we've been talking about already, which is segments or sides in this case, and angles. If we have special situation where side lengths and angle measures kind of align, we have names for those, so we can be a little bit more specific. If we have all side lengths the same, we are going to call that equilateral. Lateral coming from side, and equa coming from, of course, equal. So equilateral, and maybe I can change color here to give a little description. That means equal side lengths. If all side lengths are equal, we will call it equilateral. The next one, and it's a little bit maybe intuitive here, equiangular. Equiangular, which I'm guessing that you could guess this exactly correctly, is angle measures. Equal angle measures. I can't talk this morning. So if they have equal angles, we would say it is an equiangular polygon. And there is a case where we have both. So I'm going to stay here. What if they have equal sides and, do capital, and equal angles? Do we have a name for that? Yes, we do. It is called a regular polygon. So if we say something is a regular, so an example would be, I have a regular pentagon. I know that in that pentagon, all 5 sides are the same length, all 5 angles are the same measure. And now the fourth option here to classify, there is, and this isn't really like a classification, but I just want to let you know that this is possible. None of the above. So I don't want you to think that every polygon we ever create has to have equal sides, equal angles, or both. It could just be a normal polygon with different side lengths and different angle measures. So it could have none of those, and we wouldn't really say none of the above, but I would just wanted to make sure you knew when you draw one, you don't have to make sure that it has equal sides, equal angles. It is definitely possible to have a polygon with different sides, different angles. All right, so to classify, we also can do it, and you can see with classifying, that is the subject of these notes of how can we be specific with polygons, because you've seen them all your life, and if I'm describing one, which is going to be an activity we do, we want to make sure that we are descriptive, that we are specific, that when we communicate to our classmates, when we communicate to Mr. Keeney, or whoever it might be, that we can accurately describe the polygon so they know exactly what kind of polygon we're talking about. So this one is going to be by numbers of sides. I'm very confident that you guys remember most of these. So if we have 3 sides in a polygon, we will call that a triangle. If we have 4 sides, we will call that a quadrilateral. And with both of these two that I just wrote down, triangle and quadrilateral, we're going to have a lot of information in future units about it, specific units just dedicated to those 2 shapes. So for example, with quadrilaterals, we know we can get more specific like square, rhombus, rectangle, kite, trapezoid, but we're working more broadly, so we want to make sure we include all the polygons here, and then in the future units, we'll break down into those more specific groups. Anyway, back to 5. 5 is pentagon. 6 is hexagon. All right, let's see here. Let's go. I want to switch up colors, makes it easier. This one, I've seen 2 names in my teaching. I've been to a couple of different schools, a couple of different teachers. I've heard 2 different names. This is what I said growing up, heptagon. I've also heard this. I've also heard septagon. I am not going to lose sleep over if you say septagon, heptagon. Either one is good with me. I need to research into kind of what the story is behind that. With 8, we call that an octagon. 9 is a nonagon. 10, and then let me get this here. 10 is a decagon. And 12 is a dodecagon. Oh, I spelled it wrong, though. Let me go back. Dodecagon. There we go. My apologies. And we do have one, we never really see it, I don't know why. An 11-sided, if you want to know, is an undecagon. Again, something that I need to probably look up as to why. I'm sure the prefixes can give it away. But anyway, those are the most common ones. If you ever don't know what it is called. Another correct way, which sounds funny, but this is correct. If you have any number of sides, so if we have n number of sides, I could always say n gone. N gone. So for example, for the three-sided one, I could also call this a 3 gone because it has 3 sides. If you're having a rough day and you saw that, oh man, that's got 5 sides, what is it? I can't remember. You couldn't remember pentagon, you could call it a 5 gone, and that would be correct. Also, this is really used for if we have a 67-sided polygon. We're like, I don't know what that's called. We're just going to call it a 67 gone. So for any n meaning the number of sides, actually that's going to be a thing. N is going to be number of sides. We're going to see that a couple times throughout this unit. So anyway, on to this example here, which I believe might be our last one. It is. My goodness, quick notes. The head of a bolt is shaped like a regular hexagon. Pause. Actually, we'll probably do this whole thing. I'm going to come back to that. What markings should be added to the picture to indicate such? The expressions shown represent side lengths of the hexagon bolt. Find the length of a side. So let's do this first part here, which is what markings? What markings? And we get to talk about our friend regular. Regular, as an example, regular, or not example, as a reminder, means equal sides, equal angles. And what we also learned that if we have equal sides, we can say that they are going to be congruent sides. They are going to be congruent angles because of our definitions of angles and our congruent angles and our definition of congruent segments. So let's go ahead and show that. For our sides, we use tick marks. So I'm going to give each of these the same tick mark to show that they are the same. They are the same, they will have equal measures. And for angles, we show that with arcs. So for these angles, they're all the same. I'm going to give them the same number of arcs. And that's what it means to be regular. All the sides are the same, all the angles are the same. Mark your picture. Label, label, label your picture. All right, and now the second part is find the length of a side. Oh, my goodness, where are you going? So if I'm trying to find the length of a side here, so let's say this one, the real problem is I need to find x. And in order to find x, I usually need an equation. That's why we do Algebra 1 before geometry. We used those algebra ideas. So what I know about this picture is that they have equal side lengths. So that is where we get equation, equal. I can set an equation up. So I know that 4x plus 3, that side length has to be equal to any other side length. So let's talk about this guy. That's a side length. It's got to be equal. So it's equal to 5x minus 1. I can solve this. I'm going to take away 5x from both sides. I'm going to do that. I'm probably make some of you mad by making a negative x here. So negative x plus 3 equals negative 1. Take away 3 from both sides to get negative x equals negative 4, and we get x equals 4. I boxed it in, which, you know what, I'm going to take it away because that's not our final answer. We're trying to find the length of a side. So we're going to put it into our side length here, which is 4x plus 3. 4 times 4 plus 3, which would be 16 plus 3, which is 19. And for our units, oh, look here, we finally got units in our notes, millimeters. So 19 millimeters is our side length. If I were to plug it into this guy here, I would get the same thing just to show you. 5 times 4 minus 1, 20 minus 1, we would get 19 millimeters. So either way, we're going to be getting the same thing because this is a regular polygon. All right, that is the end of these notes. A little bit of a shorter one. Finally glad I could say that. Let me know if you guys have any questions. Thank you for watching.